Hello and welcome to the class of 5G. While 3G was built on a strong foundation of 2G, 4G decided to revamp the infrastructure of wireless communication from its deepest roots. It started with changing the network switching method. So, what used to be and what changes were made? Let's start with what it used to be. And that is circuit switch networks. Imagine that you have two geographical areas A and B. Both are fairly large and they house a number of base stations to cover the entire region, with one master switching center or MSC. BSCs talk to MSCs and MSCs talk to each other. If there is another third area, all three MSCs would communicate with one another as well. Within a particular geographic area, base station sends data streams to master. If you're wondering what is a data stream, it is a stream of encoded data sent by your mobile device in binary. These streams are then transported via towers. If a user in area A wants to connect to user from area B, he has to do it via multiple towers including MSCs, and his data stream passes through an actual physical or aerial link between these towers before being delivered to destination user for decoding. MSC takes data stream from physical BSCs one by one and switches the connection links accordingly. Such an arrangement is called circuit switch networks. The circuit switch looks something like this. They are used to apply physical switches for data stream routing. When circuit switch networks were implemented earlier, the wireless community had a lot of expectations from it. So, were they fulfilled in reality? They were created to handle rapidly growing internet traffic. But in reality, the topology wasn't as scalable as people thought. Internet grew way too fast and circuit switch networks were not sufficient to rectify the internet growth. Since circuit switch networks had dedicated physical connections, they were expected to serve more reliability. But when traffic is way too high for physical switches to perform switching operations, many connections are dropped. To overcome these issues, packet switch networks were invented. Packet switch networks ask one question and take its answer as their base philosophy. The question was, if modern smartphones work like computers, why can't they talk like computers? To expand upon it, let's say if two smartphones want to share some information like image via internet, then there are supervisors on both ends of the communication. While the sender is sending the image, it can't send it as a whole. Therefore, the image is encrypted and turned into multiple small blocks. Each of these blocks are given meta information like block number and sender-receiver details to travel smoothly. Then, the sender supervisor lets receiver supervisor know that it is sending a chunk of data in 16 blocks or packets numbered as 1 to 16 accordingly. Once the receiver is ready, the process begins. If the sender and receiver were in the same geographical area as earlier, meaning A and B, now the data can transfer to multiple paths simultaneously. Because it is divided into packets, the sequences can be corrected even if there were delays or drops on route. This whole arrangement is known as packet switch networks. Once the sending process is completed, receiver checks if all of them are present. If it comes to know that few of them were absent, it can always ask for remaining copies to the sender. After counting the number of packets, the receiver supervisor counts the order of packets. If it is messy, they can be rearranged. Then, they are decoded and decrypted and the receiver gets the same image that was sent by the sender. This is how the packet switch networks work, and this Mr. Supervisor is known as TCP or Transmission Control Protocol, which is the heart of the internet. This has multiple advantages. For example, earlier with the circuit switch spread spectrum, voice and data were treated differently and were sent on different ranges of frequencies. Now, the data and voice can be treated equally and they can travel together as well. Sending voice call data along with internet is called VoIP or Voice over Internet Protocol. Some of the applications extensively using VoIP to make free internet-based calls are Skype, Duo, Line, WhatsApp, and Hangout. And they all work pretty well. So, what are the pros and cons of such arrangement? It opens up more parallel data transmission possibilities with an opportunity to utilize spectrum more efficiently. On the other hand, the connections are not as reliable as circuit switch networks due to the links not being dedicated. It is power efficient, but it may cause latencies. And finally, it is cheaper, much cheaper. But this cost reduction comes with the price of high chances of packet losses. If we sum this up, the pros are too lucrative to let go. So ideally, the focus should be on making up for the cons. To do so, let's ask ourselves some questions. First of all, why does the connection reliability get compromised? The answer is simple. If we compare GSM and VoIP channels, a GSM channel would have dedicated users to serve who only use voice. On the other hand, VoIP channel might have both voice and data users. So, when both channels are packed, GSM easily refuses new connections while VoIP doesn't deny them, but the channel gets crowded and reduces connection reliability. Second question is, what causes latencies and losses? Let's take A to B example again. Ideally, in case of GSM connection, the data would have traveled directly from A to B on a dedicated link. But practically, even these dedicated aerial links have obstacles which can slow down the data stream. Still, mostly the content remains intact. On the other hand, VoIP makes data packets take all optimized routes. Due to varying amount of signal reflections and other hurdles, some packets might reach later compared to others, while some might fade away or not reach at all. So now we know the causes behind the issues, but what about the solutions? The solutions are quite simple though. We need to have stronger signals, which fade as less as possible with higher bandwidth and with more routes. So much so that we might also be able to send backup copies of packets instead of them getting lost. It was definitely easier demanded than done. We had reached pinnacle of what could be achieved with legacy infrastructure. So it was time to revamp it. In the next lecture, we will see how did that happen. Till then, happy learning, and I hope you have a fantastic day.